Hi everybody! Today we'll do a quick demonstration of how to work machine learning from PCA and unsupervised learning to multiple regression and supervised learning to solve a fairly complicated model that predicts house prices from a hypothetical data that simulates reality. The goal is to be aware of how an end-to-end application of machine learning can be done, going through a process that simulates the kind of messy trial and error that one may encounter in real life, and how the art and science of modeling can come together to predict prices, here on a hypothetical house pricing model. The analysts can, however, port the lessons here to other problems they may encounter in other fields. So while the focus here is on predicting house prices, it can be easily extended to other kinds of problems. The goal here is to accurately predict the price of a house by reducing the complexity of multiple influencing factors using PCA, then followed by a predictive model. So let's start with PCA. How do you actually work it in your overall work process and data analysis? I also provide an Excel add-in called Quantprof, which I developed back in 2002, and the data to be used as well will be shared so that you can all follow and do the exercises yourselves. Are you ready? Let's go! In our last session, we focused on the theoretical side of PCA by taking a look at variation via the covariance matrix and trying to find scalar or numbers in its place so that we don't need to deal with the matrix. In other words, we seek to find scalars lambda that can proxy for the covariance matrix A when multiplied to particular vector V called the Eigenvectors. Now, to simplify things from here on, we'll deal instead with the correlation matrix instead of using covariance matrices so that the metrics are comparable across variables. Plus, it'll also have an additional benefit in terms of understanding total variation measured, as you'll see below. From our last video, we know that given a form-by-form correlation matrix, there will be 4 principal components based on the 4 eigenvectors generated, plus 4 eigenvalues. Let's say we have something like this below, with the eigenvalues listed from left to right in descending order. Now, using the correlation matrix, the eigenvalues will always sum up to the number of variables, which is cool because it's easy to find not just the relative weight of each component, as we see here, but also the cumulative explained weight as principal components are added, as seen here. Thus, if we keep only principal component 1, then we capture already 50% of the variations. If we add principal component 2, then we just do principal components, we already explain 75% of the variations, etc. So now it becomes a matter of keeping only those principal components that explain most of the variations and dropping those that don't contribute that much. In return for the penalty of thrown away principal components, we have reduced dimensionality, and thus we have a more tractable problem to solve, especially for supervised machine learning like multiple regression, which we'll do later on. It's best to quickly move to an application of PCA, as focusing only on the theoretical side is of not much help once you see that we're merely deconstructing the correlation matrix into scalars called eigenvalues that give a weight to each principal component defined by the eigenvectors. So now, for this, we will use Quantprof plus some hypothetical data, and the links are provided in the description below. Now, kindly download the data, and it'll look something like this. Now, all of the variables are numerical except for address, which is categorical and gives either city or province. To make all the variables numeric, let's convert the categorical variables into numbers with 0 if it's a city and 1 if it's a province. The data would now look something like this. Now open the add-in called Quantprof Lite Just read the conditions for its use, and using the add-in means that you agree with the conditions for its use. Now, after pressing enter, go to the add-in menu and take a look at the Quantprof menu like so. Now select group statistics, then select all 4 variables from B2 to E21. The output will be provided in a new sheet. Next, from the Quantprof menu, select principal components, then select only the correlation matrix from the newly created sheet to do principal components analysis. The output will look something like this. The original matrix you use can be seen so that you can check if you use the covariance matrix or the correlation matrix as evinced by the ones in the diagonals if it's a correlation matrix. The eigenvalues or lambdas are sorted out in descending order from left to right. Do note that the eigenvalues sum up to the number of variables. Here it's 4. The eigenvectors listed from left to right as well are listed here, corresponding to the n principal components generated. Here it's 4. Eigenvectors 1 to eigenvectors 4. Then we have this curious set of eigenvectors here called loadings, short for the rotated loadings using varimax. We'll talk about that later on. So when you see the output on the left, try to imagine and take a look at it as if they were the numbers or vectors shown on the right. Now, here you can check by using matrix multiplication that indeed AV is equal to lambda V, and it gives the same output on the rightmost column. Now, this verifies that indeed these are eigenvalues and eigenvectors given matrix A, and the eigenvalues or lambdas capture the variance information contained in A all across the 4 principal components. Note also that since the loadings are rotations of the first set of computed eigenvectors, the AV equals lambda V still holds. Now, why do we do rotations? Well, the rotations maximize the variance of squared loadings within each component, meaning within each column, encouraging loadings to be either large or near zero. This leads to a simple structure where each variable loads strongly on one component and weakly on others, making components easier to interpret theoretically. From here on, we will be using the eigenvalues and the loadings instead for our analysis. As mentioned earlier, the sum of the eigenvalues when generated from the correlation matrix will sum up to the number of variables. Here it's 4. It becomes very simple to find out then the explained variation of each component as one goes from left to right. Here we stop with 2 components which already explain 94% of the variances. Now taking a look at the loadings, we find that all the variables load up highly against the first principal component. Although V1 and V2 are highly positively correlated relative to the first component, and V3 and V4 are highly negatively correlated with the first component. Meantime, V3 and V4 are positively correlated with each other, as also seen from the correlation matrix itself. For the second principal component, V1 to V3 loads somewhat against it, and it's only V4 which loads the highest against it, indicating that it's V4 which would be a good representative for the second principal component. And here we're talking about principal component as if we were referring to the columns per se. So think principal component, here it's expressed as the columns over here with the first principal component, the first column, the second principal component, the second column, and so on and so forth. Now, what have we gleaned so far? In terms of grouping, it looks like it's natural to group V1 and V2 or variables 1 and 2 together on one side and variable 3 and variable 4 on the other, thus the color scheme. So group 1, V1 and V2, group 2, V3 and V4. V1 and V2 are highly correlated, and looking at the variable names, number of bedrooms and number of bathrooms, this should not be surprising. If there are more bedrooms, the number of bathrooms are also expected to go up. Now, V3 and V4 are positively correlated with each other. This may imply that city addresses, where the V3 will tend towards 0, will have smaller sizes given the positive correlation. And conversely, provincial addresses, where V3 tends towards 1, will have larger lot sizes. However, V3 and V4 are negatively correlated with V1 and V2. It's strange to find that if there are more bedrooms or bathrooms, V1 or V2, the association is with a smaller V3, implying a city address, and a lower lot size, given the negative correlations. See the correlation matrix below. It's a bit strange, but we will explore this more later on. Let's do some data visualization. Starting with scatter plots, we can see here that V1 and V2 are positively correlated as discussed before. However, a review of the scatter plot of V3 versus V4 showed that they appear to be really two separate groups or clusters because they have two separate centers, although there is some overlap in terms of the spread of the lot sizes. In general though, the lot sizes are smaller for 0, meaning cities, while the lot sizes are bigger for 1 or provincial addresses. This shows the importance of doing cluster analysis as well, but we'll discuss that topic separately in a future video. For now, the possibility of distinct clusters involving V3 or address potentially introduces a problem called Simpson's paradox or aggregation bias in cluster data. It occurs when combining distinct clusters or subgroups into a single dataset, which causes correlations or trends to appear, disappear, or reverse compared to those observed within the individual clusters. This arises because clusters have unique internal correlations that are obscured when pooled. So lumping the data together, we have the scatter plot. Taking a look at bedrooms versus lot size, we see the negative correlation already gleaned from the PCA results, which we said to be rather strange. We said it was rather strange to find that if we have more bedrooms, we should expect a smaller lot size, which looks counterintuitive. Controlling for address, however, we have these positive correlations, meaning we do a scatter plot separately for city and for provincial addresses, and then we find the expected relationship between bedrooms and lot sizes separately. And we see that the expected relationship between bedrooms and lot sizes re-emerge. So it does appear like there was aggregation bias, lumping all the data in one set, meaning it was likely a case of Simpson's paradox because when we lump it together, the correlation was negative. However, separately, the correlations are actually positive within clusters. So it does appear like there was aggregation bias lumping all the data in one set, indicating that it's best to have a separate analysis for city and for provincial addresses rather than lumping them all together. So going back to our PCA results, we now know the following. Number one, that just using two principal components, it will explain more than 94% of the variations. Number two, to avoid multicollinearity, we can use either V1, the bedrooms, or V2, bathrooms, to represent the first principal component. We can now control for the cluster by just dropping that variable 3 from a future regression, but take care to separate the data into two groups instead, city addresses and provincial addresses. Number 4, we let variable 4 represent the second principal component, since it's the only one left with a high loading in that component. Factor analysis. If we try to do some meta-analysis, it should be fairly evident that V1 and V2 are indeed related since both have something to do with the size of the house. The bigger the size of the house, the more bedrooms and bathrooms one can fit in. So if we are to describe a factor that covers them both, we can use floor size, for example, as the factor that mostly explains variables 1 and 2 in the first principal component, and therefore we can use that to explain the first principal component itself. The second principal component is self-explanatory, that lot size is the factor and is the only variable left in the second principal component anyway. So we say that floor size and lot size are the presumed factors that explain the first two principal components given the foregoing PCA, and it captures 94% of the variations. So in the end, the output gives the summary from the PCA and factor analysis that we just did after everything is said and done. So what's our decision? Given the analysis, we drop variable 2 and let variable 1 proxy for the floor size factor, given that bathrooms will likely be a function of the number of bedrooms anyway. For example, this might be a given subject matter expert input or something that is intuitive for us. We drop variable 3, and instead of using it as a part of the variables for regression, we use it to separate the data into two clusters. Finally, we use variable 4 to represent the explicit factor lot size, so floor size and lot size. So what have we done? We reduced dimensionality by just using two variables out of the four original variables using principal components analysis. And additionally, we explained the factors, doing some sort of factor analysis. And finally, we did some cluster analysis, albeit inadvertently, which helps us to decide to separate the data by address. We are now ready for multiple regression for the prediction part, and we now drop all discussions about eigenvalues, eigenvectors, etc. as that analysis is done, and we just focus instead on the resulting decision listed here as the key takeaway. Now up next will be the more exciting part of predictive modeling using multiple regression and supervised machine learning using the analysis that we did here. Part 2 is on its way. Meantime, kindly like and subscribe to continue supporting the channel, and please feel free to comment below. See you in the next video.